So now fluorine, if you give it electron affinity, then it gains what? Electron affinity. That's how chemistry relate. Chemistry is beautiful, my dear student. So if you give it electron affinity, but this is, it means only one electron. So we give it the first electron affinity because there are the two types of electron affinity. First, second. I don't know if there is a third. You can tell me in the comment section. So first electron affinity. And then now we have fluorine, which has gained one electron. So this is the electrons gained. So that gained electrons now will be filled here. That's why that we say these negatively charged ions, they should be in octet state. So this is the octet hydrogen ion. Right? Octet hydrogen ion. So it means that if we write electronic configuration, for example, of fluorine ion, right? The electronic configuration of fluorine ions, right? So this one now will be 2:8. And this one, this is all this. This is the fundamental electron configuration. So this one now, it will be like this one. Okay, this is helium, and this is what? This is 2s, and this is 2p power 6. That's why I told you in the previous session, the prerequisite of organic chemistry is chemical bonding, which is one of the topic of general chemistry for the syllabus of United Republic of Tanzania. So if you are not aware about what I'm saying here, it means you are not aware about general chemistry. Right? Chemical bondings and even also electronic configurations is very important because they help you to understand and shift it from cramming to understanding. That is one of my objectives, to shift you, to transfer you from cramming. I'm a teacher who teach all ordinary secondary education students, advanced secondary education, advanced secondary students, diploma, college or university or institution students, and undergraduate students or bachelor students. So what I found in my research, all the students or many students in diploma who are in college level, they are learning their education by cramming. And that's the disaster. That's why that after our graduation, we cannot solve our own problems. Yes, I know that many students, they used to challenge me. So, okay, so Olenjolai, demonstrate to us what problems are you solving? Because we are graduate in Tanzanian institutions. Very good. This is the one problem that I'm solving now. You can go through this stuff yourself. So I'm solving your problem. And it's a real life problem because I'm solving a problem for people. I don't show you my certificate. However, I have many of them. Okay, so let us come to business. So you see that now. Okay, so you understood even something that you didn't understand in general chemistry. Okay, so now we can have halogen sorting ions. Okay, or halogen sorting anions. This is the one of the example of negatively charged. So what are the examples? So now we have fluorine ion. You have chlorine ion. If you understand, you just write what you have. You write with much understanding iodine ion. So these are the first examples of of negatively charged nucleophile. We have some more examples, right? Because you love chemistry, we may use symbols in writing stuff. Example, this one I should write fluorine ion, chlorine ion, bromine ion, iodide ions. That is for the kindergarten, for the fundamental students. You're an advanced student. So you have to understand what am I writing there. That's why also I'm combining text, I'm writing on the blackboard with oral. So this is called the hydroxide ion. Another example for negative charged nucleophile is cyanide ion, right? And then another example of nucleophile, negatively charged nucleophile or anions nucleophile is what? So another example is carboxylate ion. So for this one, I can write for you. Carboxylate ion. Carboxylate ion. So we have something in organic chemistry called a functional group, right? So carboxylic ions is functional group is this one. right? Or with a structure form of functional group. R means that this is hydrocarbons. R standing R representing what? R representing what? Hydrocarbon. When you say that hydrocarbon, a compound which contains what? Hydrogens and what? Hydrogens and carbon. So carboxylate ions. The fifth example is phenoxide ion. Phenoxide ion. Okay, because sometimes phenoxide ion, and this phenoxide ion, it means that phenols come from phenol, right? Phenol means that this is the phenol, right? But now, in order to formulate phenoxide ions, hydrogens, the bond between hydrogens and oxygen break, right? So that's what we call phenoxide ion. Because you love chemistry, that's why you're taking chemistry with me. Okay, phenoxide ion. Say phenoxide ion. Phenoxide ion, phenoxide ion, phenoxide ions. So remember, why am I giving you so many examples? Listen, some of the questions in the exam, they used to test you among the following elements, or among the following compounds. Identify which are nucleophile, which are electrophile, and which are what? Free radical. So you should have many examples of nucleophile as well as you can. Otherwise, you won't have, for example, that if you be given this list of compounds. So first of all, you need get separation. Don't say that, what is it? I don't know it. So you leave a blank. Okay? So that is all about, but you still have again the last one, carbonium ion. Carbonium ion, carbonium ion, carbonium ion, carbonium ion. Possibly you heard this compound when you be learning general chemistry. So carbonium ion, it contains hydrocarbons, okay? And then here we have CHE, and then we have hydrogens, but here there is no any bond, so it's negative. That's what you call the carbonium ion. So it's hydrocarbons which are rich in electron. That's the first group of ions. Did they use the Romans or they use numbers? So this number 2. Okay. So you say that a group of unsaturated compounds, second type, is group of what? Unsaturated compounds. Group of unsaturated compounds which have localized, this is new story for you, which have localized I introduced it to you yesterday, the meanings of localization and delocalization in benzene. Localize the pi bond. So this pi, write like this, pi what? Pi bond. Localize the pi bond in their functional group. In their functional group. Pi bond in their functional group. So that is the second type of nucleophile. Possibly you have never learned nucleophile or types of organic reagent in this type. Okay? So we say that this is the second type of nucleophile. We say that, let us read together, okay? And put a pause. Group of unsaturated compounds, number 1. The first vocabulary, unsaturated compounds. What are unsaturated compounds? It means if you have unsaturated compounds, we also have what? Saturated compound. So what does it mean in chemistry? Because you have love of chemistry. Okay? If you don't know about that, think and look for the answer. Which have localized the pi bond. Pi bond. Pi bond is one of the subtopic bonding in chemical bondings that I taught you about pi bond and the sigma bond, right? In their functionality group. In their functionality group. In their functionality group. In their functional group. right? So listen carefully. So this compound, so you say that so group of unsaturated compounds which have localized the pi bond in their functional group. So you say that these are the compounds, or these are the organic reactants which contain, first of all, which contain most types of bonds. We mean that pi and the sigma bond, where in their functional group. So these are the organic reactants. These are the organic reactants which contain both types of bonds, pi bond and sigma bond in their functional group. But what happens? So you say that their pi bond, it means this pi, okay, their pi bond will be delocalized, right? Delocalized around the compound. So delocalized means the position around the compound. Around the compound. Right? So you say, what happened again? Okay? So what happens? So if they contain delocalized pi bond, so sigma bond will never be delocalized. It will be there. So you see now the necessity of the sessions of chemical bond. That's why I used to teach students general chemistry first before organic, because I know how you're going to suffer on this business if you don't know about organic phase. Because first of all, pi bond and sigma bond, this become vocabularies for you. But if you know about general chemistry, being taught well, step to step, then you know that. So you say, just you pi bond, because others they used to, whenever you hear pi bond, you have to used to remember the formula of calculating the area of the circle, pi r squared, right? Since it's standard, I think it's in primary. So he said that when the positively charged particle passes near to the localized pi bond. So this in chemistry just like pi and then dash bond, right? Pi bond, compound. Pi bond what in compound. So then we say that the pi bond, so it's pi bonds, positive charging particle, positive charging particle, okay, passes near to the localized pi bond, okay. We say that then it's pi bond break. It's pi bond break, okay. It's pi bond breaks readily, okay, to donate the pi bond electrons. So we don't have only co-electrons or valence electrons, we have also pi bond electrons. That is good news. Pi bond electrons. Okay, donate pi bond electrons. Okay, release donate pi bonds electrons to the electron lava. Okay, to the electron lava, to the electrophile. To the electrophile. Nucleophile is a fundamental type of organic reactant. That's why we are spending much time on learning it. More than even electrophile and free radicals. Free radical and organic free radical and organic nucleophiles are few compared to nucleophile. So that's why we are spending much time, right? So understand that. To the electrophile. So that's what happens, right? So, to explain before I give you examples, okay, and form, yes, okay, and then after donating that ones, we say that after, okay, we say that after the nucleophile, after the nucleophile donates its bond, its pi bond electron. Okay? To what? To the electrophile. Point the electrons to the electrophile. To the electrophile. Then they form new sigma bond. New sigma bond. So while you are copying, ask yourself, what is pi bond and what is sigma bond? The second one, compare the strengths of pi bond and sigma bond. And the third question that you have to ask yourself to quick review about general chemistry. Why is pi bond breaks? Why does pi bond breaks and not sigma bond? Why both are still in the same compound? That's the question that you have to ask yourself as a lab of chemistry. So spend at least 2 minutes, pause the video, ask yourself those questions. Number one, what is pi bond? Number two, what is sigma bond? I'm not asking you to go online and try to search on Google, or maybe you have a book beside you. No. Try to think and try to remind yourself what is in your mind, not what is in your exercise book. Possibly in your exercise book or in the book, there's many informations about chemistry, but in your mind, you have nil. Okay, so you can continue to watch the video. So, I won't spend much of my time to tell you that what the pi bond or what the sigma bond, I have already done it at in chemical bonding. So you have to make sure to visit the same channel. There is a playlist called the general chemistry, and there's a playlist called the atomic structure. There's a playlist called the chemical bonding. Make sure that you dig onto this stuff, and you'll become competent enough for the rest of your life, even if you go for a higher learning institutions or colleges in chemistry, you'll enjoy the stuff. Okay? So listen. So when you compare pi bond and sigma bond, so first of all, let me explain when the positively charged particle passes. That suppose here we have a nucleophile. We say the nucleophile loves what? Nucleus, right? Nucleophile loves nucleus of an atom, right? So it's rich with electrons. So now when the positively charged particle, for example, that we have a certain positively charged particle X, passes near to the localized pi bond. So this nucleophile, for instance, that suppose that we have two compounds, compound A and compound B, but in their functional structure, there are two bonds, right? Because whenever you find pi bond, sigma bond always is there. So sigma bond, we call it the fundamental covalent bond in organic chemistry, or in covalent compounds, right? So in case that you have a single bond between two elements, that is sigma bond in case of covalent compounds, right? In case you have double bond, means one is sigma bond and one is what? Pi bond. So now if I ask you what are the examples of of compounds which contain sigma and pi bond, so you know, you begin from what? Alkene. How many examples of alkene do you know? Many. Ethene, right? Propene. So you have a lot, so now you understand, but you've been seeing like something critical. So listen, suppose that this is the general structure of a nucleophile. And we have, suppose that this is pi bond. Listen carefully. This is pi bond. I'm explaining the descriptions I've written. And this is what? Sigma bond. So this is the way that, because for you as a chemist, you forgot even how we write sigma bond. It's not more for you because you dislike chemistry, unfortunately. Or you've been told that to leave stuff in the exercise and then your brain is full with foolish stuff. Okay, so if this positively charged atom, when the positively charged particle passes near to the localized pi bond, so before this positive, when this positively charged particle is several kilometers away from the nucleophile, this pi bond is localized. So initially, the pi bond is what? Localized. What does it, so this is localized, say localized. This is localized pi bond. Right? The second process now, a stranger is coming, who is electron deficient, who is called electrophile, we're going to call it soon. Right? If it is coming, so it's approaching, Suppose that this is the nucleophile. So this is nucleophile. So I'm electrophile, I'm coming. So when it passes there, right? Then immediately the pi bonds start to delocalize. Suppose that this is localization, right? So delocalize, you find that after maybe a second is here, a second is here. So a second is here, that's the meaning of delocalization. So it's oscillatory motion, right? If you want to see its structure, it's oscillatory motion or simple harmonic motion. So it means that it has equilibrium state. So before it was in equilibrium state, now something has come and it's moving around, going this way and going this way. So because it's shifting this way and shifting this way, and this is electron lava, so it will ask you, hello guy, I came, you love nucleus, I have nucleus. Can you exchange? Yes. So what can I give you? The pi bond electrons. So now, this we call it a pi bond electrons. And let me just tell you in advance what happens, however, that I didn't teach you about the rules of body breakings. So he said that what is going to happen? So this pi bond in this state, so let me write here, A, suppose that this is pi bonds, and the bottom answer is what is sigma bond. So the bonds is going to break down. So if it's going to break down, one is going to be rich with electrons, and the other carbons, so suppose that this is carbon, for example, that in case of alkane, right? So one carbons is going to become partially positive, another partially negative. So this is electrons, rich in electrons. So it will come, hello, let us formulate. So now B and the Xe will formulate a new sigma bond. So it will form Xe and hence B, this is sigma bond. While in A and B, if it's still existing, A and B is still existing, but there's only sigma bond. It does not have what? It doesn't have what? The pi bond one cell against. So donate the pi bond electrons, and then after the nucleophile donates its pi bond electrons, okay, to the electrophile, then they form a new sigma bond. Where's that new sigma bond? This one. Where's all the sigma bond? This one. Where's the previous pi bond? This one. Do you understand? Tell me in the comment section if you have understood, or if you get troubles, tell me in the comment section. I'm here to help you. So you understood those information. Understood even more than what you thought that. Okay? So, if you've understood, I'd like to mention some examples of this nucleophile, right? The first example that I want to mention to you is all alkene. All alkenes, say alkenes. So the functional group for alkene is this one. But this one, let's say that here we have, it depends, okay? So here you can have maybe ARA, okay, but simply say that, okay, so you have a certain something else there, maybe you have ARA, but this is the functional group. What do you mean? It means that here carbon still needs some atoms, right? But our point of concentration, this is pi bond, this is, now suppose that this we say is sigma bond, this is pi bond. For the purpose of learning. It doesn't mean that the pi bond is always at the top to the sigma bond. No, for the purpose of learning and for the purpose to you to understand. But this one might be pi bond or sigma bond. Right? Okay, so our focus is this double bond between carbon. What does it mean? For instance, we have propene, right? This is one of the example of alkenes, right? So in propene, if you write this structure, we have carbon and then say double bond. Okay, so here we have one hydrogen, here we have three hydrogens, right? You have three hydrogen. And then here we have one hydrogen, and there we have one hydrogen. Right? So the nucleophile, this propene will be nucleophile only at this place. The remaining part, no any contributions to the nucleophilic property. Why? Because here we have pi bond and sigma bond. And the pi bond now, before the electrophile approaches, is localized. But once the electrophile approaches, become delocalized. Do you enjoy the beauty of chemistry? Especially advanced organic chemistry? Does it become easy for you? I think so. Tell me in the comment section. So you've understood, right? And then the second group, all alkenes. All alkenes. So now if you'll be asked to mention 20 examples of nucleophile, I think that we'll ask your teacher to ask you to mention 50 examples. Because you know, men of alkenes, men of alkynes. So if you say alkynes, the point of concentration is this one. So I would like just you to leave a simple homework before we make the next session, right? This is simple homework. This is home library study, right? Go and look in this compound, how many sigma bonds you have and how many pi bonds you have, and why. You have 3 bonds here, my dear student, right? You have 3 bonds, right? Yeah, so you say that we don't say, because this is the functional group, so you just write like this one. You have 3 bonds. So it means that either 2 are sigma or pi. So tell me, and why? I believe that you're going to do it. For example, also, we can say that butane. So if you write the structure for the butane, just for you to understand, the purpose of understanding this, we have something like this one. So this is our structure, right? So the point or the point where the nucleophilic property will act is here, regardless of what the length of that organic compound. I'm really happy and I thank God who's giving me detailed revelations of organic chemistry. I want to tell you just in advance. I think for this session, God is doing something great. 50% of what I'm teaching you is not in my exercise book. So that's it, we call it live revelation, right? Even myself, when I've been teaching this stuff for 5 years, from 2010 to 2014, I didn't teach them in this style, right? So that is God's grace. Then you need the third group? Yes, you need, I think so, because it's the foundation. Then another group is called the nitriles. And this is very important because you don't know this one. Say nitriles. Nitriles, the functional group of nitriles, this is hydrocarbon, is this one. It's a triple bond between carbon and nitrogen. We form the compounds or types of compounds called the nitriles. nitrides, right? So remember that nucleophilic is around here. Another homework again. How many pi bond we have there and how many sigma bond and why? Because these are unlike atom. These are like atom. That's a factor in chemistry. Okay? The first example. The first example is carbonyl compounds. Carbonyl compounds can act carbonyl compounds can act as what? Nucleophiles. So remember that we have a topic called carbonyl compounds. Okay? Nucleophile. What their functional group? Well, so it depends. You can have around here, you have carbon, we have double bond oxygen, and then this guy. Okay? Okay. And then other one, which possibly are familiar in state of matter, it's benzene. Special Kekule structure, right? So functional group of benzene is the functional group which is Kekule structure. So I taught you in the previous session there's a delocalizations because every end representing carbon. Carbon, 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 carbon. Then I told you that suppose that this is carbon 1, carbon 2, carbon 3, carbon 4, carbon 5, carbon 6. After a short time, delocalization takes place. So delocalization of pi bond. So means here, this is pi bond, sigma bond. Pi bond, sigma bond. Pi bond, sigma bond. Right? You are cramming. You are expert in cramming. And I will transfer you from that habit which I dislike for my life. Delocalize duty. However, that sometimes is good. Cramming sometimes is good, but not at all time. The problem we have in Africa, and especially that in Tanzania, okay, we used to give cramming the highest percent more than understanding. Because if you don't want to understand, it means that your intelligence is in vacation, it's in holiday, because it's not useful. Cramming, you just copy, you can just copy and paste in your brain. You don't trouble yourself, what does it mean? But understanding, you go around the sentence, you go around the story, you go around what you're reading. I'm not teaching about cramming and the understanding. I will teach you another way. So delocalization is taking what? Let us come back to the start. Delocalization of benzene is taking place. So if it's taking place now after a fraction of second, you find that according to the Kekule, oh, this is carbon, 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 carbon. So first is second, third, fourth, 5, 6. So you find that now the bond, okay, it is delocalized, now it is here, the other one is here, the pi bond is here. So that benzene has characteristics of delocalizing its pi bond itself. That's why that we say, finally, there is aromatic structure of benzene, which that's what we use. And having a ring, the meanings of ring is this ring, it means delocalizations of pi bond electrons in benzene is continuously taking place. So it's a ring, you see that? Okay, now this is here. That's, after time it's here. So time, you see, it's a ring, that's why we have a ring structure in benzene. But now, are you going to call your first bond benzene? Okay, many students they say no. Okay, wish you all the best. And also, to give you details that, remember that also benzene we can write in this form. Okay? You can write the structure of benzene in this form because I want you to understand. So this is carbon, this is the sigma bond, this is sigma bond, this is sigma bond, this is sigma bond. Okay, so you want now to add what is pi bond, so it's double bond. We have pi bond here, we have pi bond. Benzene should be your best friend. When you sleep during night, you have to think about benzene. You have to meditate and you have to remember about God. And also, when you're meditating, you ask God, what did you hide in benzene? Why benzene is in this world? Why am I learning benzene now? Okay? Okay, so those are the examples. So if you have any question, don't hesitate to ask me in the comment section. Okay? Then we go for the steady types of 40. This is number 3. Okay? If I gave you, I don't know that how many, I gave you what? 5 examples. So you have to go and look your own 5 examples of 40 of nucleophile, which contains the localized pi bond. Okay? I don't need lazy students. Compounds which possessing lone pair. Another types of 40 of nucleophile are compounds which possessing what? Which possessing lone pair. So if you hear the word lone pair, you have to remember our best friend who is called the chemical bonding. Because that's the point when we taught students for the first time about lone pair. We didn't mention the vocabulary of lone pair when you are in ordinary level. When you are in ordinary secondary education, we mentioned the many of vocabulary, but unfortunately we kept it quiet. We didn't mention about the lone pair. Right? Okay. Lone pair. What is lone pair? Take 30 seconds to think. What is lone pair? What is lone pair? And don't only write the definition, go around it. What does this mean? Lone pair. Lone pair means that these are the 2 electrons. Pair is something 2. 2 electrons. 2 electrons which are found where? Okay, 2 electrons which are found in the valence shell of what? Of an atom. So say that lone pair is a pair of electrons which did not participate or did not take part in the formations of 40 covalent bond. Right? Yeah. So I don't want to explain to you too much because I'm teaching about organic. I'm not teaching about lone pair. Okay. So he said that these are the nucleophile. Okay, nucleophile which are rich in what? In lone pair. Not 1 electrons. They are rich in lone pair. 1, or you can find more than 1 pair. Okay? Rich in lone pair. And then, because sometimes you can find they are rich in lone pair but they cannot donate. Okay, and if they can donate to the electrophile, which I'm going to teach you what does it mean. Right? So these are the nucleophile compounds or nucleophile reactant. Right? Reactants which are what? Rich in what? In lone pair. And they can donate. This is 10. They can donate those lone pair. They can donate what? This is still incomplete sentence because I know students that they cannot even think around. They can donate their lone pair, not 1 electrons. Their lone pair. They donate their lone pair, not in electrons or not valence electrons. They donate their lone pairs, resulting to electrons deficiency compound, or yes, or the atom compounds, okay, resulting to the electrophile. Right? Electrophile. So he said that. So we say after what? After the nucleophile, donate its lone pair, okay, its lone pair to the lone pair to the electrophile. Okay, to the electrophile. You say that then, okay, then they form what? A new bond. So the homework, they form a pi bond or a sigma bond. Examples of 40 of nucleophile which possessing lone pairs. I can also give you, in terms of the compounds, alcohols. You know alcohols. What happens if a person drinks alcohols? Okay, alcohols. Why alcohols? Because alcohols in the functional group, the functional group of alcohol is OH, right? R stands for hydrocarbons, remember that. So R stands for hydrocarbons, means the compounds contain what? Carbon and hydrogen. So these are carbon and hydrogens. It depends on the size. Maybe 1 carbon, 2 carbon, 3 carbons, depends then which alcohols are we discussing, which hydrocarbons are we discussing. So this is what making alcohol, right? So in these compounds we have how many elements? How many elements form alcohol? Basically 3. Carbon, hydrogen, and the oxygen, right? So now let me just give you a quick review. Say quick review because I love you. However, that you don't love me because you are lazy and I'm making you to struggle too much. Oxygen is number 8 in the periodic table. So it contains 8 electrons, 8 protons, and the 8 neutrons, right? So if we write this electronic configuration, advanced electronic configuration, then we begin with the older one, the form 2. Okay, 2, 6, because maybe some of the students who are taking these sessions, they didn't take my classes in general chemistry, right? 2 to 6. If now we write the advanced electronic configuration, we say that this is helium, this is 2s squared, 2p4, because 2 makes 8, right? Okay, so that's one of the methods of writing electronic configuration. By using orbital method, we say that this is helium, and then here we have what? A full pair, the orbital, and then this is 2s orbital. This is 2s orbital, and this is 2p orbital. So you have 4 electrons. 1, 2, 3. This one, this one, this one. No, excuse me. I'm sorry. Don't copy that. So according to the rules of filling electrons, we just see every orbital should be singly paired, singly filled, and then we start pairing. So you see that. So oxygen in octet state, for instance, or oxygen is forming covalent bond by using these two unpaired the orbitals, right? So it can gain, mostly it needs electrons. So these 2 electrons in px, because this is px, this is py, this is pz, according to the general chemistry, especially at concepts of electron configurations in general chemistry. So these 2 electrons of px will never participate in the normal formations of covalent bond, right? So that's why that you can write alcohol and indicate lone pair. If I could be you, I could say thank you, because I did a business that you should do in general. Okay? So that's why that we say that these are nucleophile possessing what? Lone pair. Okay? And then we have again another example is amines. Amines, according to the syllabus, we have to cover it during the Form 6 level. The functional group of amine, this is hydrocarbons, and this is NH2. This is the functional group. Let me clarify, because I know that this is the new story for you, or it's the new fact for you. So the bondings, all of these are sigma bond, right? So this is a compound containing carbon and hydrogen. So here this compound amines comprise how many basic elements? 3. Hydrogen, carbon, and nitrogen. And nitrogen is always 1. So this is what we call the amines. Okay? So nitrogen itself is elements which contain 7 electrons. So if you write electronic configurations, it means that in this, if you write the electron configurations of nitrogens, then every p orbital is unpaired. And these unpaired, 3 unpaired orbitals are the ones that will be participating in formations of covalent bond. But what happens that itself, because it will have another, so you can find that in nitrogens, these 2 electrons, these are valence electrons. So we say that oxygen, for instance, it has 2 lone pair. The first one is px, and the second one is 2s. So in order to indicate, also we say that this is what we say oxygen. So it has 2 lone pair, because these are the valence shell. So lone pair are the valence electrons, or is a pair of valence electrons, which is not used in formations of what? Covalent bond. So if example that we want from water, so you just place 1 hydrogen here, and place 1 hydrogen here, so water is formed. But these 4 electrons, which are valence electrons, which is 2 pair of electrons, is not used in formations of what? Covalent bond between oxygen and what? 2 molecules of hydrogen, and the hydrogen molecule, right? So that's why that we indicate one pair like this one for oxygen. Interesting? Tell me in the comment section. Okay, so for nitrogen, simply by following the same procedure, because you know that it contains 7 electrons, you have to show me this 1 lone pair. So it contains only 1 lone pair. So it can donate to the electrophile, right? So it means that once we have any electrophile around here, this is electron deficiency. This is rich in electrons. Okay, hello, receive, lone pair, then the new bond is what? And new compound is formed. All right? Okay. So then, the third group, we say that, to say the example, we say that ammonia gas. Do you know ammonia gas? Yes, because we introduced to you since O-level education, especially that in the topic called the chemical kinetics. Okay? Ammonia. Say ammonia. Those ammonia, this is very important when you'll be learning about Lewis and Lewis base. Okay, so I would like to leave homework 2 for this part. I'd like just you to, yes, okay? I'd like just to challenge you this simple question. So only 1 question. Okay? Do, we say that, okay, let me just ask you this way. Is there any chemical reaction, okay, reaction between 2 nucleophile, because we see that there's a reaction between nucleophile and electrophile, and then if the reason is yes, why? And the first question, and the second question is this: why alkyl halide why alkyl halides can give you its functional group, okay, are not considered as nucleophile. Now remember that halogens, there are 3 lone pair, right? Okay, are not what? Nucleophile. So explain briefly. You have to make sure that you do this homework before we meet. Okay? I didn't finish. Nucleophile is not considered as nucleophile. Why? Okay, why they have what? Why they have lone pair? The question now which I want to go and ask yourself. Okay? They have 3 lone pairs. Explain briefly. With aid of examples. Aid of examples. Okay? So why are they? They have halogens because alkyl halides, alkyl is the alkane. For example, yes, okay, it depends that is alkane or alkane or alkyl. Halides is the name derived from halogen, right? So fluorine, chlorine, bromine, iodine, they contain lone pair. Go and write this electronic configuration, the electronic configuration. They contain 3 lone pair. It means that 6 electrons, 6 valence electrons of halogens do not take part in what? Formations of simple, or we call it normal covalent bond. So they have in total 3 lone pair. Why are they not considered as nucleophile? Because they are not nucleophile. Didn't mention them. Did you mention them as an example of nucleophile? No, you haven't mentioned. Okay, so if that's the case, I would like to say that this is the end of this session, session 2. Get prepared with that. I'll be teaching you electrophile and free radicals are short, so in session 3, I'll cover them within a short time. And then we'll go the next subtopic of general introductions of organic chemistry. So I believe that you've got so much. I thank God on myself who have prepared me, and I thank God also for have given you a chance to open your mind and receive spoken and written information. Please tell us in the comment section you're enjoying this material from which school, and also from which country, from which city, from which continent. Tell me in the comment sections, so at least that I can thank God and I can notice that how far this message has spread in Tanzania, Africa, and even worldwide. So I would like to invite you in the next sessions, which is session 3 of general introductions of organic of advanced organic chemistry, so that we're going to be together and I will take you to another point. So stay blessed and stay comfortable, and may God bless you. I wish, and I'm real that I'm praying God earnestly, so that we can be together in session 3, so I can reveal a secret of what God has taught me in advanced organic chemistry. The homework that I give you, as long as I'm teaching you, or even now that you are going to have a rest, think about this issue. I'm learning this stuff in order to do what? At the end of the year. Tell me in the comment sections, but I want to warn you, don't allow your mind that in order to pass exam. Passing exam is a part of your life. But being successful in life is not measured of how many exams that you have passed. But you have to pass exams. Passing exams is not an option, but it's not your destination. It's just a one step along your journey. Because even you live longer in normal real life rather than the time you are living in school. For instance, you live 70 years. Regardless of how long, of what level of education you will end, but you'll find that the time that you spend in schools or learning is almost a half of your life. So 3/4 you are living in life. So my intentions and my safety is your success of your life from now until your departure, or until the Son of God, who is Jesus Christ, will come back and take his church, because we are hoping like that, and that's what we believe. Thank you very much. Let us meet in the next session.